Welcome back, future builders. Today we're unpacking the biggest breakthroughs in generative AI research. I'm counting down the top trending AI research papers this week. We're talking about Wan-Animate, bringing static characters to life with seamless relighting, Lyra generating dynamic 3D scenes from single videos, and OmniInsert enabling high-fidelity, mask-free video insertion. From multimodal emotion-aware talking faces in SynchroRaMa to long-term animation via InfinityHuman, we're explaining all 10 essential projects step by step. Let's dive in. Paper number 1, Wan-Animate, bringing any static character to life and embedding them seamlessly into real video scenes. Starting with the introduction, what makes this paper truly unique is the way it unifies two major tasks: animating a static character image based on a driving video and seamlessly replacing an existing character in a video with one framework, rather than treating them as separate problems. The authors build their system on top of the existing Wan model architecture, but crucially modify the input paradigm so that the same model can handle both tasks: injection of reference appearance, temporal guidance from video frames, and control signals for both body motion and facial expression. A key novelty lies in how they decouple body motion and facial expression control. For body motion, they use spatially aligned skeleton signals that map the pose from the reference video onto the target character. For facial expressions, they extract implicit latent features from the face of the source image, encoding expression but preserving identity. This dual signal approach gives the model strong controllability and expressive power. Another standout contribution is the replacement mode of the system, when the goal is not merely to animate a character in isolation, but to take a new character and replace the original actor in a video while matching the environment. To achieve this, the authors introduce an auxiliary relighting Lyra module. It adjusts the lighting and color tone of the inserted character so it blends seamlessly into the scene's original lighting and color environment. That depth of environmental integration is relatively rare in prior works. Beyond architectural cleverness, the unified input formulation is also quite elegant. The authors describe how they adapt the Wan-I2V image-to-video setup by distinguishing reference conditions versus generation regions, enabling both animation mode, character appears in new motion, and replacement mode, character is placed into the video, under the same symbolic representation. That means fewer separate models, more generality and flexibility. In summary, the uniqueness of this work lies in its combination of 1. Unified dual-mode character control, animation plus replacement, 2. Dual signal control, skeleton for body plus implicit face latents for expression, and 3. Environmental realism via relighting and color tone matching, together enabling high-fidelity, expressive, and context-aware character animations in one framework. Paper number 2, Lyra, generative 3D scene reconstruction via video-diffusion model self-distillation. What makes this paper genuinely stand out is its ability to bypass the typical requirement for large multi-view datasets in 3D reconstruction by cleverly exploiting video diffusion models and self-distillation. Traditional 3D scene reconstruction methods depend heavily on captured real-world multi-view captures, which are expensive, time-consuming, and often unavailable. This work changes the game by using a pre-trained camera-controlled video diffusion model to generate synthetic video data, then using that to train a decoder for a 3D Gaussian splatting 3D-GS representation, effectively teaching the network 3D structure without ever seeing actual ground truth multi-view 3D data. Another unique aspect is how the authors chain together a two-stage pipeline. First, an RGB decoder renders typical 2D outputs from the diffusion model, then a 3D GS decoder is trained to align its renderings with those 2D outputs, while the pre-trained diffusion encoder remains frozen. At inference time, the system drops the RGB decoder entirely, and the 3D GS decoder alone produces the 3D scene. That means from a single image or a monocular video, you can generate a fully fledged 3D scene, and even a 4D dynamic scene, with real-time rendering capability. What really pushes the envelope is the mixture of modalities: text to image, image to 3D, then video to 4D, and the fact that the generated scenes aren't just static but dynamic. You can input a monocular video and get a dynamic 3D representation. The paper even demonstrates humanoid robot simulation within those generated 3D environments, showing that the output is ready for downstream applications rather than being a toy proof of concept. In short, the novelty here lies in distilling 3D structure from 2D video diffusion, eliminating the need for multi-view datasets, enabling single image or video input to generate rich 3D 4D scenes, and opening doors for simulation, robotics, gaming, and more. Paper number 3, SynchroRaMa, lip-synchronized and emotion-aware talking face generation via multimodal emotion embedding. Imagine a system that doesn't just sync lips to speech, but truly feels what's being said, capturing the subtle tone of voice, the choice of words, and even the dynamic context of the scene. That's exactly what SynchroRaMa delivers. What makes this work unique is its ability to fuse multiple emotional signals, not only audio cues like tone and rhythm, but also textual sentiment derived from the spoken or contextual text. In most prior systems, emotion embedding comes solely from audio or image, limiting recognition of complex affective states. SynchroRaMa bridges this gap by combining audio-based emotion recognition, valence arousal features from the speech signal, and textual sentiment analysis from scene descriptions. Beyond emotion, SynchroRaMa introduces a dual input pipeline, a reference image, anchoring identity and appearance, plus a scene description generated by a large language model, LLM, to supply high-level semantic context, actions, environment, and attributes. This means the model isn't stuck with one static reference. It can respond to dynamic changes such as a character turning, shifting expression, or moving within a scene. The audio-to-motion A2M module adds another layer of realism by generating head and face motion frames aligned with the driving audio, making the avatar's movement natural and coherent. During the actual generation phase, SynchroRaMa uses a denoising UNet that integrates appearance, motion, audio projection, and the multimodal emotion embedding to produce video frames with synchronized lips, expressive emotion, and smooth motion transitions. The experimental results speak strongly. This method outperforms prior state-of-the-art models in image quality, expression preservation, and motion realism, backed by both quantitative metrics and user studies, showing higher subjective ratings for naturalness, diversity, and smoothness. In short, the combination of multimodal emotion embedding, semantic scene description, and audio-driven motion makes SynchroRaMa a standout in talking face generation, taking us a big step closer to avatars that look and feel like they're really alive. Paper number 4, OmniInsert, mask-free video insertion of any reference via diffusion transformer models. This paper introduces a highly innovative approach that pushes the boundaries of video editing by enabling mask-free insertion of arbitrary reference subjects into a target video, all while preserving natural interaction and visual coherence. What makes this work stand out is the way it tackles 3 foundational challenges that earlier methods struggled with: scarcity of training data, maintaining balance between subject and scene, subject-scene equilibrium, and achieving harmonious insertion where the added subject visually fits in the target environment. Insertion harmonization. First, the authors propose InsertPipe, a novel multi-branch data pipeline that automatically generates diverse paired data for training. This is important because realistic before and after insertion video pairs are rare yet omnipresent for high-quality editing. InsertPipe includes real capture, synthetic generation, and simulated interaction pipelines to cover real-world, generated, and complex subject-scene scenarios. Second, their core model named OmniInsert introduces a condition-specific feature injection (CFI) mechanism that distinguishes how it injects subject references versus source video context, respecting their different temporal and spatial needs. Alongside this, they employ a progressive training strategy where the model is trained in stages, from subject-only to full insertion to refined fine-tuning, and a subject-focused loss that biases learning toward preserving the inserted subject's identity and appearance. These design choices significantly help maintain equilibrium. The subject stays consistent, and the background remains undisturbed. Third, on the harmonization front, the paper integrates an insertion preference optimization (IPO) approach that uses human preference data to fine-tune the model so the insertion looks plausible, and a context-aware rephraser component at inference time, which enriches the prompt with scene-level cues to ensure the inserted subject blends seamlessly with the environment. To cap it off, the authors also contribute a new benchmark, InsertBench, to evaluate performance in this challenging task and demonstrate that OmniInsert outperforms prior commercial systems in both quantitative and qualitative tests. In short, this work is unique because it doesn't just tweak an existing video edit model, it rethinks the full pipeline from data creation to training regime to inference trick, enabling high-fidelity mask-free subject insertion in videos under diverse scenarios. Paper number 5, Beyond Video to SFX. Video-to-audio synthesis with environmentally aware speech. This paper stands out by tackling a problem that most previous systems have either ignored or only partially addressed, generating intelligible speech that is aware of the visual environment and synchronized with video content, rather than simply producing generic ambient or Foley sound. The authors introduce a novel framework, let's call it BVS, that uses a two-stage process. First, mapping video input into audio semantic tokens, a video-guided audio semantic model, and then converting those tokens into full acoustic waveforms, a semantic to acoustic model. What makes this unique is that the first stage is conditioned not just on the visual frames, but also on phonetic cues of speech, meaning the approach actively considers speaker content rather than just surrounding sound effects. Furthermore, the second stage refines those semantic tokens into detailed sound that aligns with the context of the scene. Whether it's outdoor, indoor, noisy, or quiet, the speech and background sound adapt. Another distinct aspect is the dual application. One scenario addresses video speech with context-aware background, i.e. someone speaking in a video, and the system generates speech that matches both what's being said and how the environment sounds, and a second scenario flips it. Given some audio content plus video, the system converts the background ambiance and speech context to match the visual scene. This goes beyond simply adding sound effects and enters the realm of immersive audio that is semantically aligned with both visual and speech content. In summary, this work is unique because it bridges the gap between intelligible speech synthesis, environment-aware background audio, and video synchronization in a unified pipeline. Paper number 6, OmniTry's Virtual Try-On Anything Without Masks. This paper introduces a major leap in virtual try-on by proposing a unified framework that moves beyond garments and supports any wearable object, such as jewelry, accessories, shoes, or even less conventional items. Most VTON virtual try-on systems restrict themselves to clothes and rely on explicit masks or segmentation to position items on the person. In contrast, this work eliminates the need for masks, enabling a more realistic and practical system. What makes this work unique is its two-stage training pipeline. In Stage 1, large-scale unpaired data portraits-wearing objects are used for mask-free localization. The model learns where and how to place an object without direct paired supervision. The authors cleverly repurpose an in-painting model to draw the object onto a person image given an empty mask context. Then in Stage 2, a fine-tuning step is carried out with paired data, object image plus try-on result to ensure consistency of appearance and identity of the object. This stage design allows the system to generalize to many object types with fewer paired samples. Another standout feature, the authors built and evaluate on a benchmark of 12 common wearable object classes, covering in-shop and in-the-wild images. They show that their model outperforms existing methods both in object localization, e.e. placing the item correctly, and identity preservation, e.e. maintaining object appearance in this diverse setting. The mask-free twist means users don't need manual masks or segmentation maps, making the system much more usable for real-world applications where you might want someone to try on a ring, necklace, sunglasses, or shoes via a single input photo. Overall, the value lies in generalization. Any object instead of just clothes, efficiency, fewer paired examples needed because of the unpaired stage, and practicality, mask-free, flexible. This opens up new possibilities for virtual try-on beyond fashion into accessories and multi-object scenarios. Paper number 7, Human-Centric Video Generation via Collaborative Multimodal Conditioning. Imagine being able to generate a fully realistic human video simply by supplying a text prompt, a reference image of the person, and an audio track that's exactly what this paper delivers. The standout feature here is the collaborative multimodal control. Whereas previous works struggled to handle text, image, and audio conditions all at once, this method integrates all three in a unified framework. What makes it particularly unique is how it tackles two core challenges. First, the scarcity of triplet conditioned data, text plus image audio. And second, the problem that trying to optimize for subject consistency, text alignment, and audio-visual sync simultaneously often causes trade-offs. To address the first, the authors build a bespoke multimodal data processing pipeline. They start with large-scale text-video samples, retrieve matching images that preserve subject identity but vary appearance, and further filter for audio lip-sync alignment. For the second challenge, they adopt a two-stage progressive training paradigm. Stage 1 focuses on subject preservation, making sure the person in the reference image remains consistent in the generated video without losing the ability to follow the text prompt. they use a minimal invasive image injection strategy to keep the base model's layout and text authority intact. In stage 2, they add in the audio modality, using an audio cross-attention layer and a novel focus by predicting strategy to link audio to facial motion. Importantly, they maintain the earlier subject preservation capability while adding audio-visual sync training. Another piece of innovation, during inference they introduce a time-adaptive classifier-free guidance scheme that dynamically balances the strength of text, image, and audio guidance at different denoising steps, so that layout/text control dominates early and identity/audio sync control dominates later. In summary, the novelty lies in the end-to-end, unified support for text plus image audio, the careful data pipeline to build the right training set, the stage training to avoid trade-offs, and the dynamic inference guidance to allow flexible, fine-grained control. This makes the model far more capable at generating human-centric videos, where identity, prompt, and speech all align seamlessly. Paper number 8, Vivid VR, elevating low-quality and synthetic videos into vivid, temporally consistent photorealism. This paper introduces a novel approach to video restoration by leveraging a powerful text-to-video T2V diffusion transformer, and doing so in a way that stands out from traditional methods. What makes this work unique is the concept distillation strategy. Rather than simply fine-tuning a restoration model on degraded footage, which often leads to texture loss or temporal artifacts, the authors use the pre-trained T2V model itself to synthesize training samples, embedding textual concepts, thereby distilling its conceptual understanding into the restoration pipeline. This helps preserve texture details and temporal coherence in restored videos. Another core innovation lies in the redesigned control architecture. They introduce a control feature projector that filters degradation artifacts from input video latents, thereby reducing the chance of flawed data propagating through the model. Alongside this, the dual-branch control net connector merges MLP-based feature mapping with cross-attention mechanisms for adaptive control signal retrieval, enabling both strong content preservation and flexible control. The combined effect is that the system can restore synthetic or real-world degraded videos, including user-generated content, UGC and AIGC videos, with impressive visual vividness, photorealistic textures, and smooth temporal consistency. The authors further validate their approach by introducing and using new test sets, UGC50 and AIGC50, to benchmark against existing restoration pipelines, showing clear advantages in quality. In summary, the work stands out by using generative T2V models, not just for synthesis, but as concept teachers for restoration, and by designing a tailored architecture to handle degradation control and temporal fidelity. Paper number 9, Lumen, consistent video relighting and harmonious background replacement with video generative models. This paper stands out because it addresses two difficult video editing problems simultaneously: adjusting lighting on the subject, foreground, and replacing the background, while keeping the result both visually consistent across frames and true to the original subject's appearance. Traditional methods often focus on just one aspect, say relighting, and struggle with temporal coherence, or require exact 3D models. In contrast, this work devises a clever strategy by building a mixed-domain dataset that fuses synthetic videos with full 3D control and realistic in-the-wild videos with imperfect but rich lighting contexts. The synthetic domain gives strong physical control and paired examples, while the realistic domain gives generalization to messy, uncontrolled scenarios. What really makes this project unique is the domain-aware adapter they inject into the video generative backbone. This module decouples the model's learning of relighting effects, how light should behave, from the domain appearance distribution, how realistic versus synthetic the video looks. In simpler terms, the system can learn the underlying lighting transformations from the synthetic data and then flexibly apply them to real footage without losing subject likeness or creating flickering or mismatched shadows. Moreover, the framework uses textual instructions for lighting/background control and is built on a large scale, meaning it isn't limited to one subject or one room, but is designed for general scenes, characters, and domains. Finally, the benchmark they design goes beyond simple single-frame metrics. It evaluates temporal consistency, so the subject doesn't jump visually between frames, foreground preservation, so the person stays recognizable and true to their original appearance, and background realism/harmony. Experiments show that this method produces cinematic quality relit videos that maintain the subject's identity while seamlessly integrating new backgrounds and lighting. All in all, this work is quite remarkable in bridging control, realism, and temporal stability in video relighting and background replacement. Paper number 10, InfinityHuman, towards long-term audio-driven human animation. The standout trait of this paper lies in its ability to generate high-resolution human animations of long duration driven purely by audio, which is something many prior methods struggled with. Many existing techniques that extend videos by overlapping motion frames often suffer from a drift in identity, inconsistent colors, and unstable scenes as the length increases. The authors of this work recognize these limitations and introduce a course-defined framework, first generating audio-synchronized pose sequences, which are independent of appearance and hence robust to temporal degradation, and then using a pose-guided refiner anchored by the very first frame of the video to gradually reconstruct high-resolution, long-term video. What makes this approach unique is the decoupling of pose and appearance, allowing the model to maintain consistent identity, lighting, and background even as the motion unfolds over time. By using the initial frame as a visual anchor, the system minimizes face feature drift and background instability that typically degrade longer animations. The pose-guided refiner uses stable pose sequences rather than appearance frames as the scaffolding, which in turn leads to more natural and varied hand and body motions, and better lip synchronization with the audio. Another distinctive aspect is the demonstration of minute long continuous sequences with diverse character styles, all without visible drift or scene collapse. While many audio-driven human animation systems are limited to short clips or single-style avatars, this model supports extended durations and handles diverse character appearances, while preserving identity and visual fidelity. In short, the paper's novelty lies not just in synchronizing voice-to-mouth movements, but in sustaining full-body, long-duration animations at high resolution, while preserving appearance consistency and natural gesture variation, a meaningful leap forward in audio-driven avatar generation. We've just journeyed through 10 revolutionary papers, highlighting the industry's push toward complex control, multimodality, and long-term consistency. Which of these papers excites you most for your next project? SynchroRaMa's emotion-aware talking faces, or HuMo's collaborative text-image audio generation? Let me know in the comments. Don't forget to like and subscribe for more research breakdowns.